what we're looking at is intersections of a line with a plane, right? So we spent some time talking about, you know, how do you find the vector equation of a line, parametric equation of a line, symmetric equation of a line in R3. We talked about creating Cartesian equations of planes, right? We spent some time doing that. And what we're going to look at now is the idea of intersection of a line with a plane. All right. So there's two objects that are of concern here. We have a line and we have a plane. All right. And there's three main cases here. These are the three cases. Case one is, and I mean, again, like a piece of paper comes in handy in this class, in this vectors portion, because like if you have a line, like you take a pencil, it represents your vector equation of your line, and then a piece of paper is the plane, right? There's three options. Either the plane and the line intersect at a point, illustrated in this diagram, or the line and the plane are actually parallel to one another, so they'll never cross, or the line is on the plane. Right? There exists no situation where the line crosses twice or something like that. And there's no situation where if the line and the plane are not parallel to one another, they will eventually have to cross. It's very much like, remember in grade 9, like if you have two lines, like if I have y equals 2x and I have y equals like 2.01x, those are going to cross. I mean, even if this is plus 1 and plus 10, doesn't really matter. Eventually, those two lines will cross because their slopes are not the same. All right, so here's our first example here. It says, determine the points of intersection between a line here and this plane. So the general strategy to find the point of intersection between a line and a plane is to express your line in parametric form. So if I right now I'm in vector form. So if I go to parametric form, this is going to be x equals 3 plus s, y equals 1 minus 4s, and z equals 2 minus 8s. So what you do, once you have it in parametric form, then you sub your values in here. Okay, so we have here like 4, I get rid of the x, I can change that to a 3 plus s, plus the 2, I can get rid of the y and change it to a 1 minus 4s. Oops. Minus z, I can change it to a 2 minus 8s. Minus 8 equals 0. And then based on your value of s here, and there's different values you can get, that'll like dictate what type of solution that you have. Essentially what we're doing is by subbing these x, y, and z values in, we're saying for what parameter of s exists such that this is 0, right? Because when I sub a value in and I get 0 equals 0, that must be a point of intersection, right? So I let s, I sub in these parametric equations, I solve for s, I get s equals minus 1. So I'm getting exactly one parametric value that's going to give me a solution, which means that there's exactly one point of intersection. So we're looking at case 1. -1, this will be minus -4, -8. And we get 2, 5, and 10. So that's it. I'm saying the point of intersection is 2, 5, and 10. Right? So this is a case 1 where the plane and the line intersect at exactly 2, 5, and 10. And that's it. All right, so there's one scenario. All right, let's look at another example here. Here's another example. Okay, so for this example here, it says determine the points of intersection between the line. Now this time they were kind enough, you'll see Maria, they gave us the equation already in parametric form in the plane. Okay, so you do the exact same thing. Change that y to a 2 plus 2t, change that z to a 9 plus 8t, minus 6 equals 0. So you end up getting here 4 plus 2t, minus 10 minus 10t, plus 9 plus 8t minus 6 is 0. Right, so same steps. Collecting like terms here, we got a 2t minus 10t and an 8t. That comes out to be, that gives us a 0t. and collecting up the numbers here, see what happens here, because the numbers matter too. 4 minus 10 is negative 6, minus 12 minus 3 equals 0. So I end up getting 0t equals 3. And you guys remember from a ways back, this equation has no solutions, right? There is no value of t that could no real number of t that'll satisfy this equation. So we have no solution. So there's no point of intersection. Okay, so that implies that the plane and the line must be parallel to one another. That means that we're in this scenario here, right? Case 2. The line and the plane must be parallel. Okay, so you might be wondering, is there a way to use your perpendicularness of this? Because this plane has a normal, and the line should therefore be 90 degrees to one another, correct? If it is the case that the line and the plane are like parallel, then the dot product of the direction vector with the normal should be 0. And this is method 2. Okay, guys, so now that we've gone through method 1 with you here, you can take a look at method 2. There's a second method that we can use by using the normal and the direction vector. So what I'm going to do here is I'll grab the direction vector of my line. So what do we got here? 1, 2, and 8. Take that with the dot product of my normal, so 2, negative 5, and 1. This should come out to be 0. If it is in fact, this ends up being 2 minus 10 plus 8. Okay, so what this does here, to remind you guys, is this does not prove that there's no solution yet, because I could be in the situation that I'm in case 2 or 3, right? Like if the plane is in fact parallel but not on the plane, you'll get the dot product as 0 of these two vectors. Likewise, if the plane and the line are, like if the line is on the plane, you will still get the dot product of those two as 0. So the only thing I have to do now is show that there's a point on the line that is not on the plane. So you can choose these points at random. I'm just going to take the point P, and I'll just take the initial value, like let t be 0. I'm going to get 2, 2, and 9. If I sub this into my plane here, you'll see you get 2 times 2 minus 5 times 2 plus 9 minus 6 is 0. And I get 4 minus 10 plus 9 minus 6 is 0. And in which case I get here negative 6 plus 9 minus 6 is 0. I get minus 3 is not equal to 0. So therefore, what I've done here is I've shown that here is a point 229. It's not on the plane. So either it intersects at a point or it's parallel. And I just showed that it can't intersect at a point because they're perpendicular to one another using the dot product. Okay, so that's method 2. So like the point here is that you have 2 different ways you can tackle this problem. You can either quickly take if you suspect that there is no point of intersection, you can take the dot product of the direction vector of the line and the normal of the plane. If it comes out to be 0, then either you have no solution or you have infinite solution, right? i.e. the line is on the plane. And then the only thing you have to do is show that you have a point on the plane or a point not on the plane. If there's a point not on the plane, you showed there's no solution. If you show there's a point on the plane and you've also showed the dot product is 0, then it must be the case that the whole line is on the plane. And then let's take a look here at the third example. So for the third example here, let's take a look here and see. So if I take I'm assuming, I would guess this example is going to have the line on the plane. So let's see how that would work out. If I take the direction vector 14, negative 5, negative 3, and I take the dot product with the normal 1, 1, 3, you end up getting here 14 minus 5 minus 9 is 0. So therefore, either there's no solution or it's infinite solution. Well, if you take the point 3 minus 2 and 1, that's on my line, and I sub it into my plane, you're going to get here 3 minus 2 plus 3 times 1 minus 4 is 1 plus 3 minus 4 is 0. So therefore, the line is on the plane, and therefore you must have infinite solution. So therefore infinite solution. Okay. So that's one method. Another method here, just to show you guys, is you could let x equal, I'm putting this in parametric form. And then I'm going to sub this all in. So this will be 3 plus 14s minus 2 minus 5s plus 3 times 1 minus 3s minus 4, 0 is 0. 0s equals 0. And this is true for all parameters. You see that? So that's what'll happen if you approach it using our original method. You'll end up getting like 0 equals 0, which means any parameter you choose, if I let s be 1 pi root 2 or a half, doesn't really matter, you'll get that's a point on the line. So therefore what we have here is its infinite solution. The line is on the plane. All right, that's our lesson on intersections of lines with planes.